Hey folks, how's it going? So today we're going to be taking a look at autocomplete system. So previously we looked at this system, but from a software engineering perspective, whereby we needed to scale that system to over like 10 million of users, and we were expecting 24,000 query per second. So we needed to make that much more efficient. So we delved into like some of the software engineering and computer science concepts such as trie data structure, which was an in-memory database. We spoke about how we can make updates to that. So today I thought let's look at how a machine learning engineer will approach the same problem and probably achieve the same um, scalability and as well as latency. So that's what I'm gonna do today. Is that I'm gonna be explaining this auto completion, but from a machine learning perspective. So yeah, I hope you guys find this to be interesting as well. So looking into the query auto-completion from LinkedIn. So LinkedIn followed the generate and rank architecture. So this is a very common architecture. So especially if you want to rank or suggest certain queries, like for instance, let's say you have the first stage, which is going to be the candidate, and you have the second stage, which is going to be the ranking. So the reason we have the two-stage architectures, because the first stage is just to reduce the number of candidate that we can rank. So you can imagine that here LinkedIn has like billions of queries, like right. People search on LinkedIn like probably every day. So there's new queries that comes into their search log. So now if you were about to rank like billions of queries, the system would be way, 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 way too slow. So the idea is that how can we move from billion to probably like 10 queries, right? Because 10 is much more efficient to rank. So now the first stage is just going to achieve that. It's just going to try to say, okay, we have the prefix, right? This is the prefix from the user. Like, you know, when you go to the search bar, right, you probably type your own LinkedIn, you type like SO, maybe while searching for software engineer. Then if you say SO, it's going to try to get all the queries that probably start with SO. It might not be they start with SO, maybe they contain SO along the lines, right? So the typical techniques that you might use to do this, it might be semantic search. So because of you can just like do an embedding search, or you might do something like you can have a key value search, whereby the key you're gonna make sure that all of these prefix are the keys. Then you can look up the values, which is gonna be all the uh, it's going to be all the candidates. So there's multiple ways we can do it, but we're going to talk about how LinkedIn has done it. So then the second stage is about ranking. So here you can think of like we have like those 10 queries that we spoke about, but we want to rank them like this. We can rank them based on the number of clicks. So the idea is that let's say we rank software engineer like number one, right? This is because of people we know that when we rank this, people are most likely to click on it when we rank that. So you can have three, four, five, and six. So for us to then rank this, because of the ranking stage, we can train a neural network and then optimize it to be able to rank these queries, and which is going to be something that a neural network can do very well. So we're going to get into how that can be achieved as well. Now the question becomes, can we be able to achieve the same relative latency using this two-stage architecture? With the software engineering approach, we were able to achieve the low latency using the data structure called the trie data structure, which was an in-memory data structure. So now we need to then make this architecture that we have to be much more efficient. So let's talk about those optimizations that a machine learning engineer can make. So we know that the candidate generation is that when you're given the prefix, right, we just need to return the relevant queries, right? So where are these queries stored? So these queries are going to be stored in what we call search log. So this search log is going to be keeping track of the search queries as well as their frequency, right? So you can think of this frequency is going to be a count of how many times this query has been searched through, right? The next thing from this, we just need to construct what we call the prefix and the query mapping. So this is going to be the prefix and the query. So the reason we're doing this is because we can be able to search get me top and queries. So because of we know that the queries have the frequency, so we can get like the top and queries based on that frequency. So how does this how is this achieved efficiently? So LinkedIn uses what we call the finite state transducer. So I think this is what we call also the Apache Lucency. So this is a very powerful storage. You can check it. I think it's very good for tokens as well as text. You can search it up. It's an open source project, Apache Lucent. So it's very powerful, and it, as they say, that it can actually achieve macrosecond lookup if like that's like what we intend to do. Now the question becomes, how do we then solve prefixes that do not exist in our storage, right? So we haven't constructed these prefixes probably because of they are not in our search log. So how do we solve that? Let me just take out my pen here. Sorry about this. So let's look at example like cheapest flights from Seattle to. Let's assume that this prefix is not in our storage. So one thing that LinkedIn tried to solve this problem was that they got an inspiration from Mitra and Creswell, whereby they essentially use the top two suffix, right? So let's say in this case the top two is going to be two. Then you use that suffix to search in your queries. Then you're gonna get like the relevant queries. That's what they did. But then LinkedIn found out that this solution does not yield high quality queries. So what they did was then adjusted this to adjusted the solution to create what they call suffix FST. So how they created this was that if you have a query, let's assume that you have a query like cheapest flights from Seattle to, then they're gonna like generate the suffix from this. Like let's say the first one is gonna be cheapest flights from Seattle to, flights from Seattle to, from Seattle to, something like that. So these are gonna be all their suffix. But these suffix essentially are gonna be generated from the 100 most k suffixes, like right. So 100k most frequent suffixes are gonna be collected. Because of remember that we have this frequency, so that means that the top n queries, those are the ones that we're going to be generating these suffixes from, if I'm not mistaken. So this brings us to us having the query FST. So the query FST is those queries that we generate from the search log. Then now we're going to be also having this suffix FST. So these suffix FST are going to be generated from the 100 most frequent queries within our storage. So that's what they did, right? So now to walk you an algorithm that they call the maximum content generation. So this is just a walkthrough of like how do we then generate the query list given the prefix, right? So how will this look like now? So you can think that the first step is will be like we get the suggestion, all the queries from the query FST. So like I said, the query FST is gonna be all the queries that we have constructed from our search log. So this is denoted as a FQ. So we pass our frequency, our prefix, then we get all the query list. It's possible that we might not get them. So yeah, that's something that you should keep in mind. So now we take our prefix. So as long as the prefix is not empty, so we're gonna remove the first word. Then we're gonna add that word inside this RW. Then we're gonna loop through. We're gonna get all the suffix by passing in the prefix, right? Then we're gonna append them, or we're gonna add them to the first word that we generated. So let me explain this with an example. Let's assume that we have something like software engineer, right? And the goal is to generate all the suffix. So the P, now we know that it's a software engineer. So what we do here is that we just gonna remove the first word. So we're gonna remove the software and we're gonna add it inside this RW software, right? Then we're gonna pass this P, right, to generate the suffixes. So this P, because of we remove the first word, so here it's gonna be an engineer. So then we're gonna generate the suffix for engineer. Then we're gonna add them inside this RW. But the punchline is that we're just doing this just to explain it from this explanation. So they say that for the unseen prefix, we can think of like cheapest flights from Seattle to. We try to find the suffix that start with flights from Seattle to, then from Seattle to, then Seattle to, and finally to. That's what we're doing. That's why then we just keep on removing the first word from this prefix. So we just keep on cutting it, and we're going to look there for the suffix for that. So the next thing we add them inside that. So, but I think this kind of like solve the problem whereby you can run out of prefix from the query FST. Okay, so I hope this kind of like gives you some sort of like how this how they solve the out of vocab prefix and how they kind of like construct these prefixes. So coming to the candidate ranking. So you still remember with our software engineering solution approach? So what we did was that we computed the frequency of these queries. Then every time we have to like go into the tree data structure and get the frequency and make sure that we order that, right? So we give the user the results, but they were ordered based on the frequency. But we made the assumption that, okay, you know what, the user is most likely to click on the most frequent query. But what if that's not the case, right? What if that's not the case? So that's where a neural network is going to come in handy, because a neural network, we can train it to say, given this query, is the user going to click on it or not? So we can optimize this to be able to um, to predict that, right? So that's what in this case LinkedIn actually did. So they had on their candidate ranking, they also had like some sort of like a two-stage thing whereby the first one was their unnormalized language modeling, and they had this pairwise learning to rank. So the unnormalized language modeling, essentially the goal was to compute the score for the query candidate. So you can imagine that we have these queries here that we got from the candidate generation. Then the first thing that we're going to need is that we need to score all of these. Let's say this is going to be scored like zero point 0.5 or something like that, right? So we're going to score all of this. So you can think of these scores are going to help us to rank these. Then the second stage within this candidate ranking was that they needed to have this pair was leaning to rank. So this is like we're leaning to rank objective function. So it's going to be applied on these scores, right? So this is going to be based on whether the user is most likely to click on this or whether the user is not likely to click on that query. So these are the two components that are going to be quite important. Now let's look at how these scores were computed for these queries. So they used an LSTM model in which the query scores were computed as a sequence probability. So the log probabilities of these queries were computed using this formula here. So you can think like we have the weights from the previous position, then we're going to compute the log probability of the weight at the current position. So these words from the previous position, because of this is LSTM, we can think of like we just have like the hidden states from the previous position. That's why here we have hi minus 1. So it's just the hidden states from the previous position. Then we're just going to use that to compute the log prob uh, for for the current weight. So we just do this for all the words within the query. Okay, but the punchline here is that they were trying to remove this thing here. So what happened is that Essentially, uh, when you have a weight, right? Let's say you have a weight software engineer, right? Like this is your weight at the current position. This is like I position, and the next weight that you want to predict is going to be engineer. You want to predict an engineer. That's what you want to predict, right? So to predict this weight engineer, so based on this hidden state that could have been generated, so essentially you're gonna have to then you're gonna have to like predict the probability within all the vocab, right? So let me explain this in a much more simple way, just so that I give you like a better intuition. So you can, let's imagine that you have this word as your input, software engineer, right? This is like at position I. So, and probably this word, maybe the embedding, we represent this word probably as something like 64, right? Let's just assume. So you have 1 by 64, something like that. So what happened is that, let's assume that we have like some sort of like weights here, right? So the weights will be 64. Maybe you project this to the vocab. The vocab will be, let's assume that we have the vocab of 2000. That's like the amount of unique tokens that we have. So now you're gonna do the dot product between this input, which we said is gonna be one weight by 64, which is the representation of this weight. So because of we're gonna do the dot product, so this is gonna cancel because we're gonna do multiply and add. So we're gonna be left with one to 2000. So what does this mean? It means that we computed the logic, right, across all the values within our vocab. So that's what, yeah, that's what this means. Because of what we're gonna do here is that we're gonna take this and we're gonna try to compute the softmax from this. So you can think here we're gonna exponentiate this value, then we're gonna do the sum of exponent of that value, right? So yeah, for all the values within our within the value of this thing here that we computed. So that's like an easy softmax thing. But the operation that I just did here is we call it normalization, right? So their argument is that doing that normalization is more expensive, right? So it's very, very expensive, especially if you are aiming to get like milliseconds latency. So we have to somehow remove this thing here. Um, As they say here, also, they state that, however, this natural language modeling approach is inefficient to compute the probability of the word at this position. We need to compute the normalization term. This term involves vector multiplication between the hidden states and each word in the vocab. Exactly, that's what I said. You see, like you have this word here and you needed to to multiply it against that 2000, which is the vocab that I spoke about. So that's how expensive it can be. So now what they did was that, okay, probably maybe we can introduce some sort of like scalar value, which is going to be a learnable parameter, which is b. So this is much more efficient because it's just a term that you can subtract after you do your dot product between the vector and this hidden state, right? So this dot product between these two, so you just minus this b here. So you can normalize them using this b here. So this b here is going to be a learnable parameter. So that's what the folks did to get to compute the log prop of this query. Okay, so looking at the architecture, so we can see that they had this this is how they represented everything. So you have this start token, then because of this is lstm, so you're gonna predict the next token, which is gonna be research. Then now you have the research, then you use the previous hidden state, that's why it comes here. You see this arrow, then you predict the next word, which is scientist. Then you come here, you do the same thing, and um, but that's how it pretty much works. Then you're gonna use the last hidden state right? Um, to learn to rank. I think this is the phase whereby you're gonna have to predict if this because of this is the representation of this query. So this is the representation of the queries, and you can actually predict if this is likely to be clicked or not. So this can be a very very simple binary classification like logistic regression is much more efficient in production to use. But that's that. That's how they kind of like fought that. So we looked into how LinkedIn essentially were able to build a system that could scale to the amount of users that they have, and this is quite a very very uh, good system that they had. But now they didn't cover like some of the bottlenecks, edge cases that a typical machine learning engineer will probably face. There's a lot of challenges that they face, right? Like for software engineers, they constantly have to think about availability, scalability, and latency. But for machine learning engineers, as much as they have to think about those as well, but there's certain edge cases within when you build these models that can occur. So this is what I want to get into. So this is good based on like Instacart blog. So the reason I'm using these companies like LinkedIn and Instacart is because of the best references will be these companies because they build these systems at the scale. So if we learn from what they do, it's good because of they do these things like we can see their systems are really working really well at like millions of user scale, right? So it's not actually bad to read through this these type of blogs. But anyway, the punchline is that we compose our vocab as well. When we spoke about the LinkedIn system, so we know that their vocab was coming from their search log, which is the same thing that Instacart had. Also, they had to extract 11.3 million um, queries from their product as well as brand, right? But as they did all of this, they realized that actually there were certain things that they needed to take care of. This included like removing plural duplicates. For instance, someone can search for X, someone can search for X, right? So you're gonna store these in your search log because they are pretty much different. But then you don't want to suggest plural duplicates. So you have to handle that. So we're gonna talk about the techniques that they use, as well as removing suggestions that are too long. I think that actually makes sense, and I think this is actually how the suffix technique that the LinkedIn folks have used. That long having a long prefix, it can be solved with that suffix techniques that we used, right? So it will be out of vocab then, but we will break it down into like small pieces, and that's another way we can solve this. Anyway, they say that removing suggestions with weight out of Instagram defined vocab. Yep, that also makes sense. So removing suggestion with bad width and block listed terms. Yes, this is the same thing that we spoke about when we were designing the software engineering autocomplete solution. We had a filter to filter these type of weights. So it's also important that during our data pipelines that we can like feature remove these weights. Now coming to handling missing spellings, this is a very very challenging edge case because of firstly, like when someone is typing, like that's already misspelling, right? Like because they are not done with their word. So how do you then start to search for the misspelling, right? So let's say for example I type like I want to type despite, then I type like DES. It's still misspelling, right? Because of I'm not done. So like my question is like, how do they then start to check for misspelling? So my guess will be that they maybe check the misspelling when the user is done typing. Like let's say you type, then you don't get suggestions, then they will like do the misspelling check. they'll like trigger the misspelling check thing to kind of like correct you. So that's my guess. Anyway, which algorithm they use to kind of like be able to do that? It looks like they use this fuzzy matching. So also this is an efficient algorithm. I think it uses the Levinsky distance edit. So I think the time complexity of this algorithm is gonna be log of s by minimum of between the two strings that you're trying to see if like the misspelling checks from, but that's the term complexity. So this is a very efficient. I'll definitely write an algorithm for this using Rust because I saw like you can actually approximate this algorithm. So we're gonna look into that. uh but yeah, it's pretty cool. So now looking into the semantic deduplication, I think this is a very, very, very good edge case because someone can search for, let's say, cheese slice and slice cheese. These are pretty much like similar thing. So how do we then pretty much detect it? And I think if you use some of the algorithms, they might not do a good job because of some of these algorithms like they rely on the positions of these of the weights of the characters inside these weights. So I think they did a good job to use semantic deduplication. So the idea is that you're gonna use search embedding model. So these weights, because they pretty much have semantic meaning, so they're gonna be the same in the same position on the if you're about to visualize them, right? So yeah, on the 2D visualization, so they're gonna be on the same location. So like Mario Nice, yes. So some of the techniques probably you can look into is the min hash algo is very, very, very efficient, but the problem is that it might miss the semantic thing that we spoke about. It might not take the semantic into consideration. So yeah, I think it depends on which cases, but yeah. Um, so another algorithm will probably be, obviously you can talk about these algorithms, but there some of them are much more not if are not even efficient, like lowest common sequences. These are like some of the computer science algorithms, but they're not efficient, or dynamic programming algorithm, but they might not be efficient for this type of stuff. But it's good that you know about them so that you can like raise them and yeah, anyway. So looking into the ranking stage, but for Instacart, I think I like this example because it shows that essentially you can optimize the ranking to achieve whatever objective that you want. And in this case, the folks at Instacart, they did that because you can get a business value by optimizing it to say, okay, I want you to list all the weight suggestions that will lead to the customer adding the product to cart. So we can see that they added this add to cart term there, right? So and they added this engagement. So this is still this is a click model, so that we covered also on the on LinkedIn. But yeah, I pretty much like this. So it kind of like shows that you can like tune your ranking based on your business need, and yeah, it can achieve whatever you want. So anyway, that's all I have. So I thought it should be good for me to walk you through like some of the machine learning approaches that people use, and yeah, give you like a different perspective, like kind of like take a break from software engineering. Then you look into like different architectures from a machine learning, how people solve this stuff. So without wasting time, guys, I'll see you in the next one. Without wasting any time, I'll see you in the next one.